this video, we're going to start taking a look at IMFs, or intermolecular forces. So let's do a couple things for review. Let's look at a formula for a molecule and figure out if that molecule is polar or nonpolar. And remember, it can be helpful to draw out the Lewis structures. So take a moment and try this right now with these formulas, figure out if this molecule listed is polar or nonpolar. So if you remember, polar and nonpolar refer to, does the molecule itself have poles of slightly positive and negative sides to it. So essentially, the electron density is asymmetrical in the molecule. So you really got to look at shape. Things that are linear or trigonal planar, as long as it's surrounded by the same atom, even if there's polar bonds in that molecule, the polarities are going to cancel out because of the way the molecule is oriented, and it was going to be a nonpolar molecule overall. So you really have to look at the geometry, and you might have to go review that. So for this first one here, NF3, okay, again, think of, I say snap, symmetrical molecules are nonpolar, asymmetrical molecules are polar. NF3 is asymmetrical, it's trigonal pyramidal, so that's a polar molecule. HBr has a linear shape, but it's asymmetrical. There's an H on one side, a Br on the other. They would pull on the electrons with different forces because they have different attractions and different electronegativities, so the electrons would end up being closer to Br. Br2 is nonpolar, H2O polar, methane is nonpolar, CH3Cl, which has a similar structure to methane, is tetrahedral, but now it's not surrounded by all the same atom, that would be polar. BF3 is trigonal planar, that's nonpolar. CO2 is linear, that is nonpolar. So this is just kind of a little reminder to see, do you need to review molecular polarity and the different molecular shapes? This will be coming into play in this chapter. You should be able to identify if a molecule is polar or nonpolar, because that's going to influence what types of IMFs that molecule might have. Okay, another thing for review, take a moment, pause the video, give this a try. Okay, you should also be able to tell, is a bond polar or nonpolar? So remember, if you have two different atoms with two different electronegativities, they would pull on the electrons differently, so the electrons would not be shared equally, and you would be creating a polar bond. So O and H would pull on electrons differently. They have different electronegativities. That would be a polar bond. CC, same atom, same electronegativity. That would be a nonpolar bond. Electrons would be shared equally. CO, electrons would be shared unequally, polar. And C and H, remember, even though these are different elements, we said that the electronegativity difference is negligible and that a CH bond is considered to be nonpolar. That is still something you should remember in this chapter. For the above polar bonds, which end would be partially positive and which end would be partially negative? Remember, the more electronegative atom would be the partially negative side because it would have electrons closer to it, so you'd have more electron density in that area, giving it a partial negative charge. So for this first bond, the O would be slightly negative, the H slightly positive. Remember, we can denote that with these delta, these Greek delta signs, which look like 3/4 of an 8. And CO is polar, and again, that O is slightly negative. That makes the C slightly positive. Okay. Remember your different phases, solid, liquid, and gas. Your solids are tightly packed together in a rigid form. Liquids are still pretty tightly packed, but they are able to move past each other. You're starting to have these mobile particles, and gases are very spread out, moving very quickly. So to have this rigid shape, solids have the strongest intermolecular or strongest attractive forces between particles. We call those intermolecular forces. Your liquids are strong. Your gases have minimal forces between them. Based on that kinetic molecular theory, we said there's actually negligible, though in real gases we know there might be some IMFs there. Why is this IMF chapter important? So remember that the attractions between molecules are called intermolecular forces. They're not nearly as strong as intramolecular forces, which is what's within the atom, or within the molecule. So look at these. These are water molecules. Okay, here's my oxygen atom. Here's my 2 hydrogen atoms. In this molecule, I have intramolecular forces. I have polar covalent bonds holding the O with each of the H's. The attraction between one water molecule and another, that's an intermolecular force, and that's what's going to hold these molecules together in the solid or the liquid phase. That's how solids have a definite shape and a definite volume, and that's why liquids also have a definite volume because of these attractive forces. Okay. IMFs are what really control physical properties of substances, something like boiling and melting points. When you're melting water, you're going from H2O in the solid phase to H2O in the liquid phase. You're not breaking up intramolecular forces. You are not breaking the covalent bonds. You're breaking the attractions between molecules, which lets them move a little more past each other, which changes it from solid to liquid, or which completely breaks up the IMFs and changes it from liquid to gas. It also controls vapor pressures, solubilities, surface tension, viscosities. So if you see anything about physical properties or phase changes, and you're dealing with molecular compounds, you're going to be talking about IMFs. Okay, so these are the attractive forces between molecules and electrostatic attraction. Okay, without these forces, there would be no liquids or solids. On the AP, if a question's about phase changes, you're typically going to be answering in terms of IMFs, intermolecular forces. Okay, so what are these intermolecular forces? Altogether, a lot of times these intermolecular forces are called van der Waals forces. So if you see that word, it refers to these three different types of forces, which we'll talk about: dipole-dipole, hydrogen bondings, which can be abbreviated as H bonds, and London dispersion forces, which you could abbreviate as LDF. Remember, if you're doing a free response, say what these abbreviations mean first before using them. There's also a fourth type of force called Ion-dipole, which we'll look at shortly. So what is a dipole? Remember, a dipole is just another name for a polar molecule. So one end that is slightly positive and one end that's slightly negative. So there's a separation of charge due to electronegativity differences that are not canceled out. And it has an overall dipole moment. So remember, you must have some asymmetrical distribution of charge or an asymmetrical distribution of electron density so that these polarities don't cancel out. So something like HCl. Okay, this is a polar molecule or a dipole. So Cl would be slightly negative because it's more electronegative. It would hog the electrons toward it. The H would be slightly positive. This is a polar covalent bond between them. Now I have this slight separation of charge. So what happens if another HCl molecule with the same distribution of charge comes near it? Well, this H is slightly positive, this Cl is slightly negative. There would be a force of attraction between them. This would be an intermolecular force, a force between two molecules. I'm showing this force with a dotted line so that it looks different from the covalent bonds between the H and the Cl. And you'll see that you can do a dotted line like this, or you can do a line with slashes kind of vertically, which you'll see in another diagram. But I'm just showing the difference between an IMF and an intramolecular covalent bond. Okay, so these would attract each other. The positive end of one side is attracted to the negative end of another, and vice versa. The more polar the molecule, the stronger this force will be. Now, why is this called a dipole-dipole? Because it's between a polar molecule and another polar molecule, or a dipole and a dipole. It could be between two of the same polar molecules, or it could be between two different ones, like HCl and HBr. They would be attracted to each other in the same kind of way. So very eloquently, they called it dipole-dipole force. How do I know if I have a dipole-dipole force? It's between polar molecules. So if I see two polar molecules, there would be a dipole-dipole force between them. Now, these are not as strong as covalent or ionic bonds. These are intermolecular forces, are only about 1% as strong, so very, very weak in comparison, but this is what holds together solids and liquids. This is why when you boil water, the covalent bonds, which are much, much stronger, don't get broken, but the IMFs do. Okay, now what are your most electronegative elements? Fluorine's the most, oxygen's the second most. Okay, what is your least electronegative nonmetal? Well, hydrogen is one of your least electronegative nonmetals. It's all the way on the left-hand side. It has an electronegativity of around like 2.1, depending on your source. So what they said is, hey, the strongest or the biggest separation of charge would be between hydrogen, which has a low electronegativity, and one of my most electronegative atoms like fluorine or oxygen. So they call this a special type of dipole-dipole force. They call it a hydrogen bond. So a stronger dipole-dipole force is experienced when H is bonded to NO or F, H with a NOF. We call these hydrogen bonds, which you can abbreviate as H bonds. Okay, this happens in something like water. Okay, water, the O side is my partially negative side. It's more electronegative, and I just put 2 next to the partial negative sign so that my charges cancel out to 0 since there's no charge on water itself. So if I have another water come along, the O, the slightly negative O, would be attracted to the slightly positive hydrogen in this water, and I'd have this intermolecular force, which would be a hydrogen bond. It is between an oxygen in one molecule, an NO or F, and a hydrogen in the other. Now also notice that the hydrogen that is participating is actually bonded to the NO or F in the structure as well. And this is going to be one stipulation of hydrogen bonding, that the H involved has to be bonded in the structure as well to the NO or F. Notice this time I showed the intermolecular force with, again, a dashed line, but this time with vertical dashes. How do I know if I have hydrogen bonding? It's between polar molecules where I have an H in one molecule and an NO or F and NOF in the other. Again, make sure that the hydrogen that's participating is actually bonded to the NO or F in the structure as well. So in order for molecules to hydrogen bond, here's the requirements. We said the H itself must be actually bound to the NO or F. This way, it gets the significant partial positive charge that's needed to attract the negative NO or F in the other molecule. This means that the H cannot be bonded to a carbon. If you have an H bonded to a carbon, that hydrogen cannot participate in hydrogen bonding. The other stipulation is that the NO or F must also have a lone pair of electrons, because that's the location that the hydrogen bond would form at on that NO or F. So let's look at this molecule here. Can this form hydrogen bonds? We just talked about it. Yes, water can. The NO or F has a lone pairs on it. Here's my H that's bonded to the O. Okay, that would give this O a slight negative charge, this H a slight positive charge. So if another water comes along, this hydrogen could hydrogen bond with the NO or F of the other water molecule. Okay, notice that the H itself has to be connected to the NO or F. That's how it gets its positive charge. What about this central molecule? No, this one cannot hydrogen bond. I do have an NO or F and an H in the structure, but notice that the H is not bonded to the NO or F. If I'm looking at the polarities, the bond polarities in the structure, the O is slightly negative. The carbon is slightly positive. It is not any of these H's that are slightly positive, because these are all considered to be nonpolar bonds. So if another one of these comes along, I don't have that strong partial positive charge on an H. So that's why this can't hydrogen bond. So if you remember that the H's themselves have to be connected to the NO or F to participate in hydrogen bonding, then you would understand this one. And look at this last one. Can this hydrogen bond? Yes, it can. Okay, here's my NO or F in the structure that would have a slightly negative charge. Okay, it's these hydrogens that are connected to the N that would have slight positive charges, because the nitrogen would be hogging some of the electrons away from them, and it's these hydrogens that could hydrogen bond with the N of another one of these molecules. Could these hydrogens connected to the C hydrogen bond? No, they cannot. These are all nonpolar bonds. It doesn't give that slight positive charge to the H. So remember, the H that's hydrogen bonding must be connected to the NO or F in the structure. It must have an intramolecular force on that NO or F. Okay, try this example. Which can form hydrogen bonds within a pure sample, meaning a propanol, can it form a hydrogen bond with another propanol? Yes, it can. Which part of it would form hydrogen bonds? Well, let's see. Here's my oxygen. It's bonded to an H, so this O is slightly negative, this H is slightly positive, so if another one of these come along, the O can bond with an H in the other molecule. It would be this hydrogen that hydrogen bonds. None of these H's would hydrogen bond. What about this one? No, this couldn't hydrogen bond with another one of its type, because even though it has an O and H in the structure, the H's are not connected to the O. The carbon's connected to the O. The carbon would have the slight positive charge, but it's not carbons that hydrogen bond. Okay, could these form hydrogen bonds with water? And if so, where on the structure would they form? So here's a water coming along. Okay, I have that separation of charge again, where the O is slightly negative, the H is slightly positive. So I could form a hydrogen bond between this H and this O, or I could form it between this H and this O. Remember, none of these H's would hydrogen bond, but the hydrogens that hydrogen bond could come from the water. What about propanone? This actually could hydrogen bond with water. So even though propanones could not hydrogen bond with another propanone, it could hydrogen bond with water because now the water is being the source of the hydrogen. So this hydrogen from the water, which is actually connected to the NO or F in the structure, could hydrogen bond with the oxygen that's in the propanone. Because we said the NO or F doesn't have to be connected to the H, the hydrogen bond. It's the H that has to be connected to the NO or F. That makes sense. So this oxygen, it would have lone pairs. It could hydrogen bond with this H. None of these H's would hydrogen bond. The H has to be coming from this water molecule. So what you'll notice is some molecules can't form hydrogen bonds with themselves or with like molecules, but they can with water. And that's why a lot of the times these polar molecules can dissolve in a polar solvent like water pretty well because of hydrogen bonding. Okay, so water can provide the partially positive hydrogen that's needed. Okay, this is actually why ice is so much less dense than water, because you can form this whole network of hydrogen bonds. Each of these oxygens here have two lone pairs, and then each of those lone pairs could be a source of hydrogen bonding to one of the H's of another water. And each water has two H's where there could be hydrogen bonds to the other oxygens, so you form this whole intricate network. In water, liquid water, your hydrogen bonds, since particles are moving past each other, they're constantly breaking and reforming. So you don't have this spread out network where its hydrogen bonds are stable in the solid at set angles. Okay, another type of force is London dispersion forces, which we can call a LDF. And this happens because in orbitals, in any atom or molecule, electrons are constantly moving. And though electrons repel each other, it does happen that occasionally they wind up on the same side of the atom. So let's just talk about, let's say, a helium atom. Electrons are constantly moving. At some point, they may end up on the same side. And then what happens to that side? Well, that side becomes partially negative, and the other side becomes partially positive, and it almost looks like a dipole. You've essentially created what we call an instantaneous dipole. You have something that isn't ordinarily polar, but you've created polarities to it. Now, what happens if another helium atom comes nearby to this dipole? Well, this side's negative. It would repel these electrons, okay? And it would, if you look down here, it would force the same change to happen in a nearby atom. You would induce a dipole in that atom. And this can happen in the sample of any type of molecule. This can happen in a sample of atoms. It can happen in nonpolar molecules and polar molecules alike. Okay, so it would force that same change to happen. So London dispersion forces, LDFs, are attractions between an instantaneous dipole, which happens when electrons end up on one side of the atom, and an induced dipole, something where that change induces that same change in another atom nearby or another molecule nearby. In atoms, if you have the same number of electrons, for similar sized atoms, these are typically the weakest forces because these are not charges that are present all the time. These just are induced to happen spontaneously and sometimes temporarily. Okay, so if you're considering the same number of electrons between all the types of forces we've covered, these are typically the weakest. And I say typically like that because if you do end up having a lot of electrons and they all end up on one side, these actually can become pretty significant, and we'll talk about that soon. These forces are present in all molecules. However, they are the only type of forces that are present in nonpolar molecules. So every single type of molecule has LDF as a type of intermolecular force, but they are the only type in nonpolar. Okay, how easy it is to cause this distortion is called the polarizability, or how polarizable the atom or molecule is. Large atoms with more electrons are more easily polarized and have stronger LDFs. Let's talk about why. Okay, if you have more electrons, okay, they are in higher and higher energy levels, so they are further from the nucleus. And we know back from the periodic trend chapter, if you have electrons that are further from the nucleus, if your distance increases, then your Coulombic force of attraction between the nucleus and the electrons would be smaller. So it would be easier for those electrons to move to one side, to move away from the nucleus, or to move independent of the nucleus. Also, if you have more electrons, it would result in a greater induced dipole moment. If you have more electrons, that side would be more partially negative, and it could create stronger LDFs. So the more electrons, the more easily polarized. So as the number of electrons goes up, the LDFs go up, and they get stronger and stronger, and it can actually become a really significant force. Some sources talk about molar mass. On the AP or in your explanations, you should really use number of electrons or the word polarizable, which is a great word to use as a reason for something having stronger LDFs, because it's really not the mass, it's the number of electrons. Okay, so you might ask, which has a greater LDF? Okay, they're both nonpolar molecules, so they are not going to have dipole-dipole or hydrogen bonding between them. The only type of force they would have is LDF. So the more electrons would be coming from this right one. There's more atoms in it. There's more electrons. So this right one would have a greater LDF. And you could just say because it's more polarizable, you could say due to having more electrons as well if you want an even further explanation. But they love to see this word is more polarizable. Okay, note that this induced dipole moment can actually happen when you have a polar molecule and you have bring something nonpolar next to it. It can also induce a dipole to happen. It can cause this temporary positive negative in something that's nonpolar. So we can call it a dipole-induced dipole force as well. And this is actually why something like oxygen gas dissolves in water. That's why you find oxygen in water, and that's how your fish breathe and how you have this dissolved oxygen. So you can do it with a dipole next to a polar molecule. You can even do it with an ion next to a nonpolar molecule. It can cause an ion-induced dipole moment too. So there's anytime you have something where you do have a separation of charge already, it can induce that same change in something that is nonpolar, something that doesn't ordinarily have those charges. Okay. Just a note, London dispersion forces also depend on the shape of the molecule. So the more surface area you have for contact, the greater the LDFs. So something that is like a long chain has more surface area than something that's spherical, because you have a lot of the surface area kind of hidden inside of this spherical molecule. So the more surface area you have, the more points of contact, so the more LDFs you can create. Okay. Just a summary. So we said all molecules would land inside here. All molecules have LDFs, any type of molecule, polar or nonpolar. If you now have a polar molecule, you not only have LDFs, you're not only within this big circle, you're in this smaller circle here too. You would also have dipole-dipole. And if you're comparing the same number of electrons, typically dipole-dipole is stronger than LDF. Okay. Again, if you start having really a lot of electrons, LDF can overpower dipole-dipole. But typically for the same number of electrons, dipole-dipole is stronger than LDF. Okay, now if you have a polar molecule, but it has an H in one molecule and an NO or F in the other, and remember the requirements, then you not only have LDF, you not only have dipole-dipole, you also have hydrogen bonding. So it's kind of additive. It's additive forces. Okay, just the last type of force, ion-dipole. You can also have an ion attracting a dipole. Dipole, you have a slight separation of charge. Okay, right? Something like water. You have partial positives, partial negatives. Ions have positives and negatives. So if you have something like NaCl, okay, Na is positive, it would be attracted to the O side of water. Cl is negative, it would be attracted to the H side of water. And this would be an ion-dipole force. Again, very elegant. Ion-dipole. Okay, these are actually pretty strong. It's the strongest type of IMF of the ones we've just talked about, and this is why ionic compounds tend to dissolve in water. Okay, how do I know if I have ion-dipole? It's between an ion and a dipole, ionic and water. So if you see NaCl put in water, that is an ion-dipole force between the ion and the water, because remember, a lot of times ionic compounds dissociate in water. Just a quick question, what kind of forces between ions in the ionic solid in NaCl? Remember that those are ionic bonds. That's an intramolecular force that is way, way, way stronger than the IMFs. Okay, so remember it's Coulomb's law when we're talking about ionic compounds. Smaller distance or smaller radius, bigger charge would have a stronger force of attraction. It's going to be about IMFs for molecular compounds. Okay, so relative strength when comparing particles with similar numbers of electrons only. Typically LDF would be the weakest, dipole slightly stronger, hydrogen bonding stronger than that, ion-dipole the strongest because you actually have a full charge in the ion. Again, there could be differences if you're not comparing the same numbers of electrons. If you were then looking at strength between molecules that have the same type of IMF present, then the more electrons you have, the more polarizable it would be, and the stronger the IMFs because the LDFs would outweigh the other. And we'll look at that in terms of strength soon. Okay, so we'll come back to this slide, but in case you're wondering about strength right now, here's your relative strengths. Okay, again, just watch out. Nonpolar molecules with significant numbers of electrons can have really strong LDFs between them that could potentially outweigh hydrogen bonding or dipole-dipole forces. Okay, so here's a summary. Okay, there's a lot. Let's summarize it. If you have a nonpolar molecule, what kind of IMF do you have? LDF only, London dispersion forces. If it's polar, ask yourself, does it have an H with a NOF? And remember the requirements. If no, then it has dipole-dipole because it's polar, and it also has LDF. We said all molecules have LDF. If it is polar and has an H with a NOF, and the H is actually bonded to the N or F, and the N or F has lone pairs, then it has hydrogen bonds. And it also has dipole-dipole, and it also has LDF, but typically hydrogen bonds are the strongest, so that's the most prevalent. If you have an ion and a polar molecule, you have ion-dipole, and if you have an ionic compound, remember that it's ionic bonds between them. Okay, if you put that ionic compound in water, then there'd be ion-dipole between the ions and the water. Okay, and I kind of put this in order of weakest down to strongest if you're comparing similar numbers of electrons. Okay, you might want to take a moment to try these examples. So for practice, KBr with H2O. Okay, KBr is ionic, H2O is polar, so you have ions with polar, that's ion-dipole. NH3 with NH3. Okay, these are trigonal pyramidal, so these are polar molecules. You have an H bonded to an NO or F, so it's polar with an H with a NOF, so it's hydrogen bonding. It would also have dipole-dipole. It would also have LDF, but I'm asking about which is most prevalent, so I'm just going to pick the strongest type. Okay, CCl4 is nonpolar, I2 is nonpolar, so that would only have LDF. NH3 is polar, H2O is polar. Okay, let's ask myself, does it have an H with a NOF? It does. Does it meet the requirements? Yes, this is hydrogen bonding. HCl with HBr, this is polar, this is polar. Does it have an H with a NOF? No, I don't have the NOF, so this is just dipole-dipole because it's polar. It would also have LDF too, but I just asked from what's most prevalent. He with He, that's just a single atom. Okay, that's got to be nonpolar, so this would be London dispersion. Take a moment and try these the same thing. First one is polar, second one's polar. Does it have an H with a NOF? Yep, so this is hydrogen bonding. NF3 with NF3, these are polar, trigonal pyramidal. So these are polar and polar. Does it have an H with a NOF? Nope, so it's dipole-dipole. Here's an ion with something that's polar, ion-dipole. These are trigonal planar, so these are both nonpolar, so this is London dispersion. HF with HF, these are both polar. Does it have an H with a NOF? Yep, so it's hydrogen bonding. This CO2 is nonpolar with nonpolar, that's just London dispersion. OCl2 is a bent shape, so this is polar, Does it have an H with a NOF? Nope, so it's dipole-dipole. Hopefully this helps you review intermolecular forces.